In this example, we want to graph the function g of x equals 2 minus the square root of negative x squared plus 6x plus 16. Now, this is a very odd function to graph unless you know what's essentially a trick to it. But this trick is useful anytime you have something of the form square root with an x squared in it and a bunch of other stuff that you're trying to graph. Some f of x equals that. Right? It kind of raises the flag of you need to use this technique that I'm about to show you to graph it. And what we'll do here is essentially figure out what this thing looks like, and from there we'll be able to graph it. So we're not going to plot points or anything like that. Instead, let's write this g of x as y. Now I'm going to subtract the 2 from the other side. Y minus 2 equals negative square root of all this stuff. Negative x squared plus 6x plus 16. Squared, by the way. Okay. And one thing to note right here is this negative. That's going to matter later because there's going to be two cases, one positive and one negative, and we happen to be working with the negative case here. Well, what we're going to do next is square it out. Square both sides, and that's where we lose this negative. So I'm going to leave this left side as y minus 2 quantity squared, and then the right side becomes negative x squared plus 6x plus 16. Next, I'm going to bring all the x's over to the left side, leaving just that 16 on the right-hand side. So this gives us, let's see, how about x squared minus 6x? Okay, then I'm going to leave some space, plus y minus 2 quantity squared equals 16. And you can maybe see where this is going here. So I'm going to use completing the square on these x terms here, which is where you take the linear term or the b term, or you can think of it as the term just connected to the single x and not the x squared. You take that term, 6. You could also take negative 6. It doesn't matter because we're going to divide by 2 and then square that result. You always do the same thing. Take the term, divide by 2, and square it. So 6 divided by 2 is 3. Squared is 9. So plus 9, plus 9. I'm adding 9 to both sides. So now we have a perfect square trinomial, we call that on the left. So that's x minus 3 quantity squared plus y minus 2 quantity squared equals 25. And now we can see that this is indeed a circle, with the center at, let's see here, center would be 3, 2, and the radius is 5. Why is that the case? Well, a circle is of the form x minus h squared plus y minus k squared equals r squared, with the center is hk, and the radius is r. Now we are ready to graph this, but we're not going to graph the whole circle because this is only a half circle. If we were to work our way back to the y variable, so we're essentially working this whole thing backwards, we'd essentially come to a point where we need to take the square root of both sides right here. And then we would have to do a plus or minus, right? Plus or minus, because when you take the square root as part of solving a problem, you have to add on a plus or minus. But if we put on plus or minus, that makes it not a function anymore. So we can only choose one or the other, and this specific example already chose the negative. So we're stuck with the negative. So what does that tell us about this graph? It's not a full circle, and it's not the top half of a circle. The negative means it's indeed the bottom half of a circle. Given that, we can now graph this thing. Okay, so we have a center of 3, 2, so that's right about here. And then we have a radius of 5, so I'll go over 5 to the right. That brings us to 8. To the left by 5, that brings us to negative 2. And down 5, that brings us to negative 3. Remember, we don't have to do the top half. And connect all these up to get a nice half circle like that. From here, we can easily compute the domain and range. Remember, the domain is the x values covered by the function, so I'm thinking here we have negative 2 up to 8, and those are inclusive, so I'd use the hard brackets. And range, now I'm looking at the y-axis, how about negative 3 up to 2? Right, so imagine how hard it would have been to compute the domain and range without knowing the graph. We would have spent quite a while looking at this function, plugging in different points and trying to figure out its behavior. But with the graph, notice that it's very quick to get the domain and range.